Start the stream. There we go. And if people come late, all right, that's fine. I'm not really upset if that happens. I just want to make sure that I reward you for being here. You want to start with some good news that not everybody's going to hear? Really good news? There's no class next week. But then you have class for a week, and then the following week after that, no class the next week. So if you look at the next 3 weeks after today, 2 of them are with no class. How about that? That's some good news.
I will start crying now.
Oh, it's okay. You don't have to cry. I mean, I miss you too, but it's okay. You can relive the highlights on YouTube.
She wants to know about homework.
Oh.
Yeah, so is the homework then due next Friday? Or is it
No, not next Friday. It'll be
after?
a week after.
Okay.
It's a 2-week deal. I don't want you to do it over. You can do it in a week, I'm pretty sure. It's like the first homework without the derivation. But we'll talk about that today. There we go. Did I check the stream? I didn't check the stream. What am I doing? It's Friday also. Another piece of good news. It's Friday. You like Fridays? Anyone going anywhere for spring break?
Bellevue, Iowa.
Woo!
Bellevue, Iowa, or Bellevue, Nebraska? Iowa. I think there's another one. I don't know. My husband has arranged everything.
Okay.
He's like, we're going. Wait, what's there?
You can share when you come back. So we have some.
Yeah, what is there in Bellevue?
I have no idea. There was a B&B who liked, there might be water activities.
So it is like a little trip.
Yeah.
That's good.
I'm going to Nebraska.
That's good.
That's Nebraska if you speak 2-year-old.
4-year-old.
But that's what he started saying it.
Yeah, it's true. And it's just continued. And we don't want to correct him because it's cute.
We're gonna party in Omaha.
Yeah.
Omaha is my Omaha.
You're going to.
It's not my Omaha.
The end of the week.
Yeah. I'm going to Lawrence, Kansas.
You're going to.
Well, let's try to clean out the rest of the house. We might actually have a sale on our house.
Hey.
Yay!
So good news all around.
Yeah.
Yep.
He's throwing the rest of the stuff in the car that didn't fit the last time.
You know, if I had a truck, I wouldn't have to make this trip. Anyway, it's a long-running joke.
Not happening.
So, where were we? This week's been like a mess for me because I had a midweek trip to Salt Lake City. I'm overhearing. I want to hear this conversation.
So,
Ariel, are you on my side? Could you help me out here?
He doesn't understand either, and I was explaining that my father thinks every man needs a pickup truck, and he's like, oh, like Cynthia's dad.
All right.
They're of the same.
While we're chit-chatting here, do you want to see my first car?
yeah. Come on.
Yeah, he had a Trar. That's what we used to call
It looked
him.
almost exactly like this baby right here.
Are you serious?
It's 1977 Chevy El Camino. Now I had this in, oh yeah. I thought, you know what it needs? I need to put some bass in it because there's like 2 seats. I had gone to a swap meet and bought really terrible speakers and put them behind
We
there.
need to get a view from the back. That way
Oh,
we can
pardon
see
me.
the full truck
It's
there.
truck in the front. I'm sorry, truck in the back and car in the front.
It's a Trar.
Half truck, half car. They haven't, so like all these other cars from this era have come back, you know, you start to see like the Beetle. I guess they still have Camaros that have never run away.
So California.
Oh,
See, but this makes me know when I think in California, thinking El
well,
Camino.
so the El Camino, yeah, exactly. I think, El Camino Real, which is the road that connected the missions south of where I was. But yeah, so this started it all off. But I guess this is why I can go both ways. I have a car, I have a truck. I can have a truck.
You're not getting the Trar.
No, I know. I can't justify it. Although there's the little boy in me is like, yeah.
See, I want the muscle car.
Oh,
No.
I had a wimpy muscle car. I had a 2-seater once, and that didn't do well either. No, I'm just gonna be with the Dadmobile now. All right, should we have class? Is that what we're here for?
I thought so.
Class. Where were we? What do you remember from last time?
Where were we?
Just asking what we remember from last
The
time.
Bayesian's cheat model thing.
Cheat model thing. I don't know that they cheated.
Well, they use ML estimates for
Yeah.
the saturated model, which is like sort of cheater.
That like drives me mad. Like you're gonna take your Bayesian model, fit it to data, generate data from it, and be like, well, does it look like the data? And the way you look at data is like, well, forget Bayes, I'm going to look at data with ML. That's a little weird, right? But that's what happens. I don't know. It's kind of funny because you quickly get into the discussion of what's a model versus not. Is a correlation a model? Is a covariance a model? I would say there's a model that implies those.
We call it the saturated model.
That's right. So shall we just kind of pick up where we were? Let me just give the highlights. Today we are going to be done with CFA though. This is the last stand of CFA. And I'm going to repeat this. In reality, I don't know why anyone ever does CFA. I'm serious.
But you say the same about TFM.
Yeah, well, the idea that most of the data that you see in our line of work is continuous is absurd.
Okay. Yeah. Okay.
That's really what I'm after.
Yeah, items aren't usually.
Why I'm making that really, I did this also. If any of you went to the seminar I gave in Wan Chan's thing, I was like, let me provoke a little bit of it. Let me just say something really provocative, because that like gets your attention and makes you all mad. But I think that's sort of it. Like in psychometrics, how much of our data are continuous? There are some. Reaction time, if you have response time, reaction time.
Slider bars.
Man.
Well, they're bounded.
Uh-huh.
It's continuous
Okay.
between the bounds.
Okay. Yeah. So the pure off-the-shelf CFA, you get using with continuous data, and then you're like, oh, but my data, they're not continuous, but they're close. Right? We talked about this the first time, but CFA for me is the reason why people use it is that IRT is actually much more difficult to make work, even though you wouldn't think that. But in a typical case, item response theory, item factor analysis, they're harder to make work, particularly when you have small sample sizes. If you're trying to estimate certain numbers of thresholds or intercept parameters, and you don't have a lot of sample, you're in trouble. But Bayes helps that.
CFA with ordinal data, you wouldn't call it CFA?
No.
I call it item.
Well, item response theory.
Okay.
But then at some point, what's the model? I mean, the model data likelihood is what I'm attacking here. If you think of Bayes' theorem, let's do this. Let's forget about the label, because once we start labeling things, that's bad. Let's just forget that. But if we say we have a model, and again, we're doing the Bayes' theorem thing here, right? Let's say that the distribution of our data, given all of our parameters, that's my theta right there, is proportional to, actually forget this line, there. We got distribution of parameters. Actually, I'm completely blanking on a Friday. My gosh. What am I saying? I need to go back and delete this YouTube. The posterior distribution of our parameters given our data is distributions of data given parameter times prior distribution of parameters. All right. So what I'm really talking about is this thing right here. In psychometrics, in the type of data that we have, particularly in this example, we're saying it's normal, right? And it's got some type of mean vector and covariance matrix. These data aren't normal, right? And it's not even they're not normal. You can sort of argue that the distributional approximation could be there. It's the biggest thing to me, which is they're just not continuous. They're not even the same sample space, right? And I think that's the hard part for me. So that's why I say you can't do this distribution with the data that we have, because bad things happen. That's more precisely. What CFA is, let's leave that for someone else to argue. Be more technical.
You can do it, you shouldn't.
Yeah, right. It could be really bad.
Yeah, it'll let you.
Absolutely. So, what do you think? Why do people use this distribution then?
That's just what you're talking about now.
I would say it's easy, because the model nearly always converges, runs within seconds, estimates with ML quickly. Things are awesome, but not.
It is easy.
What?
It is easy, but
Model fit is also easy, also true, right? So we have a big, and I would say as a teacher, I think if I'm going to teach you latent trait or psychometric models, excuse me, something fell in my eye. If I'm going to teach you this stuff, I'd rather start with the CFA version because it's much cleaner. We don't have the link functions getting in the way. We don't have all sorts of weird information things to deal with, although information, anybody know the information function in CFA? Item information? It's flat. When you take IRT, they're like, look, all right, here's theta, like your ability parameter theta, and here's the item information for theta. And they're like, look, you can find a peak, right? And you want to find those items. If you were to compare, so this is a binary item, let's say, right? If it was a polytomous, you might see multiple peaks or multiple areas. The CFA analog of that would look like this, right here. The item and trait are independent. So our item information is flat. You can write an item information without respect to trait. Why is that important? Well, think of it this way. If you have CFA and you're trying to build a computerized adaptive test, wouldn't really be that adaptive, right? Second, there usually is, and this is usual, there's usually a really big gap between what that flat line happens to be and the other line. And the reason for that, it comes from just the idea of what information is contained in the variable. If you have a truly continuous variable, then every little tiny epsilon you might move around is a different value of that, and that would be essentially where information is. You can pinpoint precision where that happens to be. If you've got a binary item, you have 0 or 1. That's it, right? So it's not a lot of information there. So IRT likes I feel like the people who have taught IRT like, oh, look at that, we can design items. But truly, if you were to design items, if you could design things that were continuous, they would have more information. If you could, that's the hard part. So anyway, so I'm just rambling now. So, but yeah. Oh, the other part that I was going to say is, yeah, but this is suspect because really, do you actually have continuous data? Like more often than not, you'll get a line, you'll be like, look at that, really high information pretending it's continuous, but really it should look like something like this. That's sort of the joke with all of it. So that's going to lead to a couple things. You're going to overestimate the precision of your latent variable. One of them. So anyway, I'm arguing this today. I'm giving that provocative thing. Why do people use CFA or why do people use this assumption for their model data likelihood, right? Come on now, right here, this one, for not continuous data. When I would say, like, the counter to that is Bayes will make it better. Bayes will fix everything. Not really. But it will help you with estimation. I can tell you that much. You may be able to estimate models in Bayes that you couldn't estimate in marginal maximum likelihood. And I said may. So there's another part of Bayes that's kind of funny. This came up a little bit yesterday in the conversation with a couple of people. I talked about it on the way home with you, Lisa. You can specify, we've seen this before in your homework when I said, oh, I'm drawing on my laptop. It's not working. This is when we did the homework with the multiple the regression, the linear model. You had to go and problem 3 said, what if this effectively was equal to a constant, or 1 or 1 times 1 over sigma squared, right? So it's constant, right? It's flat. Think of it this way in Bayes, for identification, the reverse could happen. When you identify a model, if you're thinking like, how many items do I need in a CFA to identify a factor? The typical idea is 3. But when it comes to Bayes, no, it's not. It's not there. You can identify the factor. You could identify a model where you say your model data likelihood is a 1 and you actually have a prior distribution for it. Right? Because it's possible you didn't collect any data. Let's say I have a normal 0, 1 as a prior. That's an identified model now. So identification in Bayes, model identification is a really interesting topic because you can identify things. The context of this came up with was, we'd look at that homework problem where I had you do the heterogeneous variance. I if you think about it, how many people do you need to estimate that model? And then each group, effectively, you need enough people to find a variance parameter, right? So I think that's just the easy way of putting it. There's probably much more elegant ways mathematically to phrase that. But technically speaking, that's from a frequentist point of view. You could specify that as a prior, not have that information in your data, and you still can find a posterior distribution. Crazy, right? So that's actually one of the knocks on Bayes. I'm rambling today. One of the knocks on Bayes is you can really quickly identify a model that you otherwise wouldn't be identified otherwise. So is that good or bad?
Sounds like voodoo.
Well, it's a nice, how do we want to put this? It can be voodoo if you're claiming that your posterior distribution based on a normal, like if you did this, you said the prior is normal 0, 1, oh yeah, I forgot to collect the data, so therefore my posterior distribution is effectively normal 0, 1, or somewhere proportional to that. If you claim that that's truly a posterior distribution, that's bad. But if you write out your prior and write out your data likelihood and you actually like show it, you put all this stuff there, you can describe it that way. No. I know. I'm trying to think of a way where it would be good. The other part of it is, there is, in psychometric models, it's bad because there is that lack of identification that can happen. And we saw this when we saw multiple modes before in that first analysis. So priors can help get you out of that as well. So there's sort of this weird confluence of things. Anyway, let's go back. Any questions about what I was just talking about? I'm just going to run code. This is our first try at model. Remember, it blew up. In that it had the multiple mode issue, right? Ding. All done. Oh, look at that. That's terrible. All these values that are bad. And then over here. Yeah, that's right. This is showing. Look at that. These factor scores are bad. That basically says they're coming from distributions that have bimodal issues, and that was the issue with our last model. We went and marker item identified it, and then reran it. There's a little bit of an adaptation for one of the parameters for the variance for the factor. But technically, I think you could get by without it if you were to draw the algorithm out. So, yeah, Bayes, you can quickly get an unidentified model identified, which is a problem because if you're like, oh, this didn't work, let me tighten my priors, you might just be fooling yourself about the priors, right? It's a tough thing to know. Look at that, it worked, hooray. We're all happy. Now, posterior predictive model check. Remember what we did for that? I said, I think at the end of last Friday, I am out of it. I'm ready for spring break. Spring break, Kansas. If you remember the last time, we said the path to nirvana, didn't I say? The first step on the path to nirvana is model or chain convergence. But the next step after that is model fit. And the final step after that is your model has a story to tell. Really. I guess every model has a story to tell. The question is it interesting enough to publish? So step 2, model fit. We said, okay, here's how, let's take these posterior predictive model checks and try to take a look at what they do with respect to your data. You're basically trying to say, let's imagine that my model was the true model. Let's generate a bunch of data sets with that. And for each data set, let's take some summary statistics and compare them with what we would see with the data themselves. Right? So what we're going to do is we're going to take 5,000 simulated data sets. I picked 5,000 because it sounded really big. Sometimes that may be too little. Sometimes it may be too much. It depends on your model size. I used some code to do that. Do you want me to go through the code one more time just to kind of refresh our memory? Because the model object that's in the posterior, this right here is a list. Right? So it has 4 chains, but they're in different spots it's a little, I didn't want to sample from the chain and then sample from the iteration within the chain. I'm just going to take each of those chains, each of those parts of the list, and glue them 1, 2, 3, 4 into a big matrix. And that's what this command right here does, creating a very big matrix, which is 4,000. So I had a chain length of, I believe, 3,000 with a 2,000 burn-in for each of these models. So I have a 4,000 total chain length, and the 209 is the total number of parameters I had. To go and create the data from the analysis, I needed to, so each one of these simulations, we have to go and take our model parameters, consider them true, and create data from them. So to do that, I had to go and pick out the values of the parameters that were needed in the chain. So all this set of syntax right here tells me the columns in this big data matrix that contain the mu parameters, the loading, so this is the item intercept, excuse me, mu is item intercept, lambda is factor loading, bless you. Psi is unique variance, and phi is the factor variance. So those are all those parameters. And then I create a whole bunch of objects to save the chain variance. By the way, I'm creating the object to begin with. I'm creating a big matrix. Alternatively, in a loop, this is one of the R, little bits of R knowledge if you're trying to figure out R. If you could append, you could start off with a null object, and every time you go through an iteration, you could glue another line to it, but that becomes increasingly slow at the size of your object, because every time it has to copy a big one, add another line to it, and then basically copy it twice. So if you create a matrix that's the size of the object to begin with, and you fill that in, it goes faster. That's just a little bit tidbit of R knowledge there. There are probably other ways that are more efficient than that, but that's just trying to give you the loop without having to go and use the apply function within class. Saving a bunch of objects. Okay, so now this is the simulation part right here. We draw an iteration at random. Right, 658, that's our iteration. We grab the mu's, the lambdas, the psi's, and the phi's from that iteration. So these are the current values of the item intercepts for that iteration. These are the current values of the factor loadings for that iteration. You can see the first item is our marker item. We're going to go and combine those and use the marginal model, marginal data distribution, to generate a brand new data set. So here we've got mu, the mean vector is mu, the covariance matrix is lambda phi lambda transpose plus psi. And actually we're going to go and save. So this is our current chain's assumption of what the true value for the population data should be. All right, so these are the mean vectors right there. The covariance matrix then looks like this, right? So we can then save the covariances, right? This command right here just takes that covariance matrix and makes it into a big long vector. Right, so we had 10, covariance matrix is a 10 by 10 matrix before, and we just made it into 100 by 1. In this case, R saves it as what's called an atomic vector, which isn't really something you can do matrix algebra with. It's just a set of numbers. Then we simulate our data from our multivariate normal. So we now have a new data set. Look at that. By the way, I'm just looking at one of these variables. This is where I'm saying CFA is ridiculous. Like, not only are we not just seeing integer values for all of our scores, we've got things that are negative, right? We've got, let me see, I don't know that I see things above the range over here yet, though.
So these are like the items.
These are the items. These are the actual, like, that's right. If you collected another sample of people that had this spec, these specs for what you were doing, this is what you would expect their data to look like. What's that? 5 was the biggest.
So if you go a little there, you have it was in one column with 5 points.
Okay, so yeah, so you can see our data is going out of bounds. It's going all over the place. It's continuous. So this already is sort of, right? This is sort of along the lines of when Lisa teaches this class. You put kind of what you expect, the expected value for each kind of level of theta for what an item should be, right?
Yeah, so my version of why continuous is silly is that it's a linear model. The line keeps going. And so to me, the problem is that it's a linear model for relationship between the item response and theta. It needs to be nonlinear because it needs to understand that it can't go past 1 and 5.
Makes sense.
It needs to asymptote.
Are we following? Any questions on this so far? Do you remember this? Okay, yeah, that's exactly it. So this is sort of doing that, right? We're getting the same. It's a different mechanism. So we're generating data randomly, but we can see that it's sort of not fitting already. I'm saving just the top triangle of the correlation matrix. And then I'm going to calculate a few statistics. By the way, your homework this week, you'll have a standardized root mean squared residual. So some of this code you can use to do that, okay? And I'm making you do it because, again, I like to think Bayes helps you learn other models, right? And so this is going to help you have to understand where things are. You're welcome to use this specific version of standardized root mean squared residual. In my quest to give you the most accurate information I could in building this, there's like 40 different formulas for what people say a standardized root mean squared residual is. M pluses involves in a model similar to this, M plus will also involve the mean vector. Even though they're on a different scale, it'll be there. Let's see if I can find that link. I don't think I put it in here though. I'll have to look it up at break. I believe that was the case, but that came from like a late night before I did this. So anyway, what am I doing here? I'm calculating the standardized root mean squared residual for this one iteration. Now, standardized root mean squared residual, that is comparing our simulated data covariance matrix with the covariance matrix from the data that we collected. And it is trying to come up with a statistic that represents kind of a standardized difference for each of those cells, right? So for a given cell of the covariance matrix, what is the kind of standardized difference between what we have and what we had in our simulated data and what we had in our real data, observed data? Yeah.
Is it including the variances too?
Yes, it is.
Okay, because those can be off,
Yes, they can.
unlike
That's right. Unlike in your CFA model, where you have saturated variances for the unique variances, and you typically have no, unless you put a constraint on the variance parameters, you don't have any discrepancy in the diagonal between your model implied covariance matrix and what you have in the data. Here, we will have a discrepancy. In fact, this right here is you can see down the diagonal, that's actually where our biggest discrepancies are falling right now. Some of those are fairly large.
So then under the same logic, wouldn't it make sense to include the means because those could be off?
Those also could be off, yes.
So, but this doesn't? Or
This doesn't, no.
Okay.
This was trying to split the difference with the book, but I actually believe the book's formula for this was different from the other one that I thought it should be. I think what you tend to standardize by. What's the denominator? Does it come from your observed variances or your simulated variances is the difficulty. So this is standardizing by observed variance right here. These are things that I didn't go back and think about when I was doing things in CFA. It's like, oh, there's a formula. Actually, no, there's quite a few. Okay, so same thing we could do with the roots mean square error of approximation. This formula is the comparison of our covariance matrix from our simulated data to our covariance matrix from our observed data. Now, remember, each of these covariance matrices that we're forming from simulated and observed is actually an MLE. That's tough, right? So the covariance matrix, actually, is it MLE or is it a, it's not an MLE, pardon me, in our simulated data. Or when we use the cove function, MLE would be covariant, it would be the sum of squares and cross products divided by n. We have, I think the covariance formula uses the unbiased version for the variances. So it'd be n minus 1.
It's the Remele?
It's the Remel version of it, yeah. And yet another statistic. But it's not a Bayes statistic, right? So that's sort of weird. The other thing that we note is that every time that we calculate these statistics throughout this sequence, we have this, no worries, they have this data covariance matrix that doesn't change. It's like saying, oh, the truth is the data covariance matrix. Regardless of that we had 177 people in our sample, this is true, right? So, are we familiar with this? Once again, the steps, I'm going to do this one more time. I'm not going to go through it, but I'm just going to tell you, as it's simulating, for each, we draw, for 5,000 replications, in my case, we draw a one iteration of the chain values. And again, we're drawing an iteration because it allows us to have the posterior distributions be correlated. Okay. We then create data based on what our model parameters from that iteration think the data are. We then take a summary, in our case, covariance matrix of the data, and we do multiple comparisons with it and the covariance matrix of our observed data, right? So we have the simulated data covariance matrix, we have the observed data covariance matrix. Here we're collecting standardized root mean squared residual, which is a global measure of model fit, root mean squared residual, root mean squared error of approximation, RMSEA, which is another global, and then for each correlation, we're basically going to compare the distribution of our correlations in simulated data to the distribution of correlations from real data. Posterior predictive model check. Questions? Okay, this is what we had for our histogram of standardized root mean squared residual. Right there, our density. And then we saw the root mean square error of approximation was a little bit higher. And then we went through and looked at all the correlations themselves, right? Here's the first correlation, which is the correlation between items 1 and 2 in the data. All right, sorry, this is simulated, right? Here's the density of our simulated correlation. Look at the range of this thing, right? That's basically, our model is saying that our correlation between these items is somewhere between, I don't know, 0.25 and 0.65. This, by the way, is a great thing that I also learned from Bayes, which is it takes when we say psychometrics are large-scale statistics, it's because if you think of, again, it's an ML frequentist type idea, but let's switch to frequentist because it's going to suit me here. The idea of a sampling distribution. If we were to go and collect 177 people from the same population repeatedly, and then go look at this correlation, it would likely have some type of range that looked like this too, right? It's really hard. The sampling distribution, the variance, the sampling distribution of the covariance is really big. Right? You don't really talk about it a whole lot in statistics. I don't know if you talk about it much at all, at least in places I've been, maybe over in the stat department.
But we make a big deal about that in meta-analysis.
That's good. That's good.
Can I ask a question
Yeah.
about that? So if you were to calculate like a confidence interval for a correlation using frequentist methods, would it be that big or would it be smaller?
I don't know.
Well, it's hard to tell, yes.
Depends on my priors.
I say become an empirical question to some extent.
Mm-hmm. I would expect it, because I'm having very diffuse priors. There's a couple ways why I can't tell you, because this comes from a model. This is not direct correlation. There may be something in the model that's causing it to be bigger than I expect. So maybe there's some parameters that are harder to estimate that's causing this wiggle. I would expect it to look similar though. But we can find out. I'm about to go estimate a saturated model where we go estimate that. Why don't we go look at that? So the true correlation, I just said that. This is the fault that we lie into. But this is the reality of the posterior. So like the framing of the posterior model predictive model check is truth is in your data. But like studying statistics, that's just another estimator, right? That's another estimate, right? That's the problem I have. We're going to go and I'm going to go argue for why that may not be the case. But if anyone wants to work on a research project, this is an area we could jump in really quick. But this actually was, this is quantiles this needs to be SimCore. These are the quantiles of this correlation right here. We generated data once with a 100% correlation. So this is data core, pardon me. It's not, yeah, data core, no, it's sim core. What am I doing? There we go. The reason why it looked like that before was the correlation of 1. I actually went and took a correlation matrix. When I put it to quantile, it vectorized it and it said, let me go look at the quantiles of this. Well, the diagonal of that correlation matrix caused this result, so that's not really true. This one right here is what I'm looking for. This is the range. The interquartile range is 0.4 to 0.5, which isn't too bad. The median's 0.46. Anyway, somewhat interesting how this all works out. There we go. So we can also go and do quantiles. And last time I looked at, so if you're going to go look at this and say, yeah, I don't think I have good model fit, then the next step to go into is drill into these correlations is usually what people talk about per item, and say, wait a minute, which are the items that are most discrepant from what the data correlation happens to be? And in this case, what I'm calling about discrepancy is I'm looking at the percentile. If I were to convert where this red line is, which is our data correlation, as a percentile in compared with our distribution from simulation, I want to take the percentiles that are up in the upper side 0.25 or the lower 0.25 to make that work. So these are the ones that I flagged that are above 0.975 and below 0.025. Here's some questions I can't answer for you though. If this was truly correct, like if we knew in the data, let's just pretend this is like a typical homework assignment I'm going to give you. I generated some data and gave it to you, so I know what truth is. I don't know how many you would expect to see here with that same flag. I don't have a proper reference distribution in my head. I don't know what's normative. So I have that hard time understanding how many is too many. It's tough.
Can you say again what this means?
Yeah. So this is the set of correlations in the data. I'm sorry, in our simulation. Set of correlations between items where our data correlation was either in the upper tail, the upper 2.5%, or the lower 2.5%.
Okay.
Right? So here's our observed correlation. This is our data correlation. 0.6 here. This is between items 1 and 2 again, the top one. 0.6 is what we observed. In our simulation, we found the correlation mean to be about 0.45. The median was 0.46. But this observed value was at the 97, almost 98 percentile. So that's why it got flagged as being that. Right? So when I look at this, if I'm going to go and say which items don't work, I don't know, what do you think? Which items don't work? Let me ask. If this is telling us where our CFA model, our one-factor model, is not fitting our data, where are the items that are most suspect? What shows up the most in these pairs is a really crude way of looking at that, right?
Yeah.
Item 1 shows up in 3 pairs. Item 2 shows up in 1, 2, 3, 4, plus with 1 here, that's 5, right? So these are indicators of what may not fit. And if you're in operational testing and you really need to have a test because that's what's paying your bills, like, hey, those items, they're out, right? So.
Or we look for clumps to try and figure out where there's multidimensionality.
If you're trying to figure out where you should modify your model, that would also say, hey,
Like 1, 2, and 10.
1, 2, and 10. What is there about 1, 2, and then you go back to the items and say, what is it about 1, 2, and 10? Item 1, invasion of Iraq. Item 2, something about Middle East. Number 10, punishing America for its sins. This is the problem with doing post hoc model modification, which doesn't mean it shouldn't be done, but it's subjective. It may be highly biased based on this particular sample, and we're not exactly sure how it generalizes. But at some point in your life, you probably will have to do it. In fact, the reality of it is we change the model most of the times. Yeah.
But the issue of generalization, yes, in my mind, it's like it's always there, yes?
Model misfit.
Huh?
What's always there?
The generalization.
Oh, yeah, that's for sure, yeah.
You know, because when we talk about sampling from a population, it's sampling what? Sampling the items, sampling pieces of the construct, sampling the units, the individuals.
Mm-hmm.
It becomes always, a lot, in my mind at least, more complex than what we make it.
Oh, yeah, by far. Yeah, this is one piece of evidence, but this is shaky at best. If you publish this, let's say we publish this and all of a sudden people are using this to go and identify, I don't know what, people with really extreme views. I don't know why you wanted to identify them, but let's imagine, you can know the survey, right? You publish, somebody, help me out here, get in the history of the surveys you've worked with, ask. I shouldn't say that too loud. I don't want to pick on too many, but you know how it works. You start with one article and that sounds good, and maybe you're able to get more people using it, and more people are using it, but they're using your established norms based on a sample that you did. And things start to fall off the rail pretty quick, and then at some point it becomes, well, you look back and all the evidence looks like this, but everybody's using it in this other way that doesn't fit with data, but you can't change it from here because that's bad, right? Do you know what I'm saying?
Yeah. I mean, in clinical assessment happens all the time. If you're using norms that were not the best to start with.
Exactly.
Diagnosis is terrible.
Oh yeah, yeah. So it's sort of the base of it. So how about we look at this from a different perspective? Let's keep talking about, I put this in here because I just want to say it brings up a couple other issues in the sampling of this. And one is, let's go pretend that we didn't just have a point estimate from our data. Let's go and see if we can get a model to work. Now this is somewhat dangerous in that I'm going to put a prior on this model for my mean vector, my covariance matrix. And that might bias the model from what we would get from an MLE perspective, which in the long run is unbiased, but for any given point estimate, particularly for a small sample like we have, small-ish sample, may not be good. So in CFA, there's the concept of the saturated model. And by saturated, I mean, this is the model where you estimate every mean, every variance, and every covariance, right? And so in a multivariate normal distribution, every CFA model that you can create will be nested within the saturated model. Meaning, you can now have a good model comparison. I mean, and this is where the basis for the logic of the model, particularly the likelihood ratio test in a frequentist setting, comes from, is that because the saturated model subsumes the CFA model. It's a catchphrase I use a lot, but it's a big concept in what we do.
It's the answer key.
It's right. It is the answer key. That means if you fit the right model, your model and the saturated model are going to look the same, right? And that's where the analysis is. So saturated model is like, oh, I could use this all the time and I'd be fine because it has all the answers, relatively speaking, right? So the saturated model is one where we have to go and use a multivariate normal. We're going to estimate a mean vector. We're going to estimate a covariance matrix. And that latter part, the covariance matrix, is where things get a little bit more complicated in the Bayes world. Because this prior distribution for the covariance matrix is not as easy to do. It's not as easy to see how it works. But let's give this a try. Questions, first of all. See, they're going to come and arrest me for my prior. The Bayes police are coming. So I came back from a trip. I'm going to tell you a personal anecdote, man. Sure. I was coming back from a trip to Salt Lake. I went to Salt Lake City Tuesday, came back Wednesday. I was coming back, like 10 o'clock Wednesday night, and I'm wanting to get home. I'm not paying attention. I was trying to drive slow because I figured it's likely to be caught. And I'm in North Liberty, and I do a 52 and a 35. So I get to meet some of North Liberty's finest, and I was very, as my typical MO with every traffic stop, I want to make sure that the officer feels comfortable, not threatened, and of course conciliatory because he's not the adjudicator, he's enforcing the law. I'm not, so hands always visible, tell him where things are. I think it didn't hurt that I was dressed in a suit with a tie also at the time. And he comes back and he gives me a warning.
Oh, nice.
Lucky. So I was very apologetic anyway. I was thinking of, I mean, I earned it. I admitted it. And I was thinking about how I could use this as a teaching tool for my son, because I broke the rules and now I have to, deal with the consequences of it. And then I got lucky. So anyway, hearing that made me tell a story. So my prior distribution of getting the ticket, I thought I was going to get a pretty nice ticket out of it. So.
The Bayesian police had all of that too.
I know, the Bayes police.
The machine back there.
Yeah. Yeah. All right. Okay. So what we're going to do with this is we have to talk a little bit about what's the distribution, what are the prior distributions that we're going to do here. So let's do our Bayes trick. That's right, the Bayes police in this machine. I know what you're talking about. That machine.
Yeah.
They're listening to me. Ariel, maybe you should think about taking my survey. People hear me. They have microphones embedded in my office. I'm just messing with you. No, I'm.
You know what they say about paranoia, though?
What's that?
If people are really out to get you, then paranoia is just good sense.
There you go. And not only that, paranoia is the saturated model. Because it fits with both or neither. So it subsumes normal. Anyway, sorry. We have so our data, we're basically saying the distribution, what we're looking for here is the posterior distribution of, I'm just going to put X bar and sigma. These are our mean vector and covariance matrix given our data, right? That's our posterior distribution. We're going to put this proportional to the distribution of our data given X bar and sigma. Sigma times the prior of X bar and sigma, right? So this right here, the distribution of our data conditional on X bar and sigma is what? This is tough in some respects, because if you're like, yeah, estimate a mean vector and covariance matrix, there are quite a few distributions where you could go and do that with data. So this is the first step. So I'm going to pick the distribution of this that matches the saturated model that we have in CFA. Right? And that is, this thing is multivariate normal. Right? And basically we're saying with a mean vector and a covariance matrix. It's just that. So you have a multivariate normal density. Right? So for every y, you plug in the mean vector, you plug in the covariance matrix, you get a vector of data, and it tells you the height on this 10-dimensional distribution. We good with that? So that's the hard part about figuring out what the saturated model in Bayes is. We could have chosen a different distribution altogether. We could have chosen one that was categorical. We could have chosen one that was bounded in some way, truncated normal even. All of them would give us a mean vector and a covariance matrix. But I'm choosing to use the one that parallels CFA in this case, and that's yet another interesting part with it. All right, for the prior, right here, let's talk about it. The prior of X bar and sigma. Now, I phrased this as a joint prior, but because we're in multivariate normal land, this is a generalization of what we did with our linear model. You remember the prior for the linear model? When we said, oh, we can take the prior of beta and sigma squared error and put them in a little bit different form. Right? So in this analog, X bar here is our beta. We're effectively fitting a very interesting linear model that has a mean for each variable. Right? And I should have called it y bar or mu or something, since my data are y. Sorry about my notation, but just like in linear model land, we can break this down to be the following. We can take a condition. We can say that we have to form a conditional prior for the mean. So that given our covariance matrix here, that's our analog of sigma squared, the mean vector has a distribution. And then we also have a marginal prior for the covariance matrix itself. Okay? Kind of weird, but
What
that
do you mean by marginal in that sentence?
it means that regardless of the mean vector, this is our prior for, it's not conditional on what the value of the mean vector is.
Okay, but the means are conditional on covariance.
That's right. So, what do you think? What should our prior be for this first part right here? What's our prior for our mean vector? Now think of it as individually, each mean is univariate normal. Or sorry, I just gave it away. Individually, each mean could be, by analog, univariate normal.
Given that, I have one option.
Okay. We usually say this is multivariate normal, right? With a given prior mean, geez, I'm running out of letters. Don't want to use sigma. I'll call this V of mu 0, right? So what we have to do, what we can say here is that for all the means, we have 10 means in this case, we can use a multivariate normal prior. We can pick a prior mean vector, right, which means this is our prior mean, the elements of it is our prior mean for each item's mean, right? And we can pick a covariance matrix as well. If we follow along with my philosophy of uninformative priors, like we would in a linear model, we would say the means are 0. And the variances, the covariance matrix would be diagonal. We would say there's no covariance as a prior between the means, but that the diagonal elements, the variances for this would be really large, like a variance of 1,000,000, right?
Why would you make the means independent of each other?
Well, you wouldn't. You don't have to. But I think the question would be, do you do more harm in saying there's no correlation,
I got you.
or do you do more harm in saying there is correlation?
Okay.
And this is where the idea of the Jeffreys prior would come in. The Jeffreys prior would effectively make even though you're saying it's uniform likely, actually no, that's not the right, never mind. I'm going, there are priors that you could specify that try to give you that empirical correlation in it, but that's just not, in this case, not one.
No, but it's a good point if you don't have information yet.
Yeah, and so the reality of it is we're trying to pick this thing such that there's so little information in it that it doesn't affect the mean. So what I would say here is this thing is a vector of zeros, right? And then this thing is a diagonal matrix with 1,000,000 down the diagonal, right? And 0 in the off diagonals. And that sort of maps onto what we did with our beta vector in the univariate world, in the linear regression that we did before. How we doing? See, one thing I would argue with here is, do we want the mean at 0? Because we know in our data the mean has to be between 1 and 5.
Yeah.
So I could probably move the mean to 3. But the reality is, here, let's take a look. What is the height of the normal distribution at 0 versus the height at 3? Let's try this. D norm. X is going to be 0. Here the mean is 0. And the standard deviation is the square root, because I can't do it off the top of my head, of right here. Right? So that's the value, that's the height of the distribution of the prior at 0 when we have a mean of 0. Actually, pardon me. I wanted to say, and this is the height of it at 3. You see where we start to diverge? It's the 7th decimal place, right? So that's with a mean of 0. If I change that mean to 3, you're going to quickly see that the height is point something and 0.5 versus something and 2.3. So the reality of it is, when I pick the covariance matrix in this way, the influence of the prior on the means that we've picked is out in the 9th decimal place. Right? So it should have a very minuscule impact on the choice because basically if we were to draw a mean of, if we were to sample this mean and it were to be somewhere around this range between 1 and 5, you're not going to see a big difference in the numbers. Does that help, Lisa? Okay.
Is there a value that you could pick for the variances that would be too big that it would cause problems?
At some point, you run into numerical precision issues, right? What that number is, let me find out. Usually there is a, there we go. Here's the largest possible number you can have as a floating point. Actually, no, hold on, here it is right here.
So that's what infinity means according to R.
That's it, right? So there it is. That's the maximum value you can have. And this is where I'm saying if I'm specifying a uniform prior across the real number line that's improper. That's the improper one. But there's nothing, a proper uniform is to say between negative that and positive that. And all of a sudden it becomes proper. But yeah, that's the biggest one. I don't know where that is. The other problem is if you have, when you do a division, if you say, so you can still get a number when you divide by that one. 1 over. But if I do plus, oh, no, doesn't do it. Never mind. Anyway, so.
And you're picking
Normal.
distribution so that this is
Conjugate.
divisible?
It's conjugate prior. Yes, it is.
As opposed to uniform or something.
That's right. I could have done a uniform if I wanted to. Other questions on this choice? Is this all right? Are we good? Mostly? So? Because it's about to get really weird. We're about to go off the rails. Right? So I'd rather give you that firm edge of the cliff, right, before jumping off the cliff, instead of like one of those things like where the rocks are really crumbling. It's a bad example. That's like the scree crap that you see in EFA, right?
Yeah.
I think scree literally means crap. All right. Okay. How about the covariance matrix? Are you ready? What is the distribution for the covariance matrix? The prior. So here's where things get weird. We know with one variable, if we were doing this with the first item, in a univariate normal, we know that the variance parameter there, we could have directly mapped from our linear model example. Right? We said variances follow, to make a conjugate prior, we could have picked an inverse gamma distribution for the variance. Now again, inverse gamma for the variance, because Jagg's phrases it as 1 over the variance, it's actually a gamma distribution, right? And do you remember how we did that when about doing that before? We said, okay, what's the maximum value of the variance? And then we tried to pick a very uninformative or diffuse gamma distribution. What we need is the multivariate analog of inverse gamma, right? And that turns out to be that for this covariance matrix, what we're going to look for is the inverse Wishart distribution. Have you heard of an inverse Wishart before?
I think I saw it in some random article a while ago.
Anytime that you see multivariate normal in Bayesian, almost always you will see inverse Wishart. Not always. There are some cases where you wouldn't do this. But inverse Wishart is the conjugate prior for the covariance matrix in the multivariate normal. What do I mean by that? Right, when you combine a multivariate normal for the means for a prior with an inverse Wishart prior for the covariance matrix, along with your model data likelihood of multivariate normal, then the posterior means that you're going to sample from a multivariate normal for the mean and from an inverse Wishart for the covariance matrix. So it becomes conjugate prior. We can make a very efficient chain out of that. Now the distribution itself is crazy.
Yeah, I'm on Wikipedia, and it looks pretty scary.
This is the distribution, and it's nearly impossible to plot. But this is the distribution here. What?
There's a big man in it, that can't be good.
Yeah. So It's true. So what this is a distribution that's used when you compare it with, so X here is not data. X here is like our covariance matrix, right? So this is where we're saying, let's imagine, so remember what the prior distribution says, right? Let's pick a value of the parameter and go see how likely that is to occur. For us, our parameter is a covariance matrix. Right? So we plug this matrix into this function. So X for us is our example covariance matrix. We plug it in here. There are two parameters. There is this capital psi matrix, and there is this nu parameter. Nu is very similar. Remember in inverse gamma we had the alpha beta, but we were able to express those in degrees of freedom effectively and projected value of variance. Nu is our analog to the degrees of freedom, right? So very small values of nu will have very diffuse values for the value the prior itself. Sigma, or this psi matrix, though, that is effectively like our analog for the variance in the inverse gamma. Right? So what did I have to do in the inverse gamma? So what I did, I said to make a very diffuse inverse gamma, let's go figure out the variance of y first, right? And we're going to plug that in as our prior value of variance, because that's the maximum it could be in a linear model, right? And then let's go say I have 1 degree of freedom, because that's the minimum I would have. When we put those two together, I get this very diffuse value of the prior for any variance I would pick. The analog here for that would be to say I have 1 degree of freedom for nu, and I have a diagonal matrix where the variances are what I'm looking at in my data already.
What does degrees of freedom mean? Because I don't think it means number of variables.
No, the way that it was phrased in the inverse gamma, and why I'm saying that,
I
is
wasn't here that day.
no problem. It's okay. Why it was thought of as kind of your degrees of freedom error, or your degrees of freedom error in a linear model.
Okay.
So think of it this way: it's how much data you have to make this specification about your prior distribution or your posterior distribution.
Okay.
Right? So that's effectively it. So you pick one, you're like, I have 2 people. Right? I'm going to make a variance out of 2 people. What's the sampling distribution of a variance with 2 people? Right? Very broad. That's why I'm saying that. So inverse Wishart's nuts. And now the other thing that's nuts about this is try to plot it. Because the data, so what inverse Wishart returns, so if you go and do this, if you were to go and take this, let's just take, for example, let's take a diagonal covariance matrix, again, with the variances of all of our variables down the diagonal as our psi matrix here. And let's take 1 as our nu parameter. So we would say, okay, let's go take a given covariance matrix that could be out there, right? We have to make it positive definite. And when that happens, then the likelihood or the height of that PDF is given by this function right here.
And the multivariate gamma is no pretty either.
No, none of it's pretty.
So, terminology question.
Mhm.
You did a gamma for 1 variance.
Mhm.
Why don't you pick multivariate? Is multivariate gamma a thing, like for more than 1 variance?
You could, yes, but inverse Wishart's the conjugate prior. It's sort of an analog. And when you get into gammas versus chi-square versus Wishart, there's a lot of similarity between them. So an inverse gamma is also a scaled chi-square, sometimes called this.
Okay.
And this parameter right here is not a distribution, although there is a multivariate gamma distribution. And I believe it probably is Wishart, but I may be wrong. I may be wrong about that. But this is a multivariate gamma function, right? So this is not necessarily a distribution. It's like a constant that comes out.
That is related to distribution.
It is, yes. You can make it a distribution in terms of the parameter. Oh, terrible.
And the gamma have also connection with the beta. Gamma functions have connection with beta functions.
That's right, yes.
So you can also go into that route, but it gets all, it gives me bad memories from when I was in grad school.
Yeah, well, we don't need to, let's not have bad memories from this. Let's just make this work for our purposes. Sounds good? Here's the thing that we have to think about. I can't even plot this distribution for you because I have a covariance matrix. Even if I took a 2x2 covariance matrix, there are 3 parameters. To plot a multivariate distribution in 3 dimensions, I'd have to make to look at what the prior is, right? Actually, I have to do 4 because the height. I'd have a 4-dimensional surface to plot even, right? So even if I wanted to, I couldn't plot this for you. But I can tell you a couple key bits of trivia that may help feed in what we know. In the multivariate, in this, pardon me, one thing I need to note, this new parameter needs to be at least equal to the number of variables in your data to make it work. But one of the pieces of trivia, this actually in the textbook we have, is this, the inverse Wisher. If you plug in a diagonal matrix here, and this is equal to the number of variables you have, then what that does is it puts a uniform prior on your covariances. It's like saying the range of the covariances is effectively, uniform prior on correlation. If you look at all the correlation matrices that could be attached to your covariance matrix, the prior for correlation is uniform. So it's very uninformative, right? So that's when, again, you have diagonal matrix for psi and nu equal to the number of variables you have. So there's not a whole lot after that I can tell you about it. It's tough.
So I'm trying to think of this like from my limited understanding of matrix algebra and statistics. So forgive me, because I did not learn this in graduate school. So good for you for actually trying to learn this shit. I wish I would.
This what?
I speak disparagingly of things that are hard for me. So you have like you're trying to find the matrix. So there's like the mean of the matrix, like what the best guess for each parameter is.
Mm-hmm.
Is that in here somewhere?
You can figure that out from the moments, but I can just show you.
Okay.
The mean is given by the following, right? So if you pick nu to be number of variables plus 1, then what you end up getting is the mean will be that matrix that you plug in.
Things on the diagonal.
Mm-hmm.
So that's like your best guess.
Mm-hmm.
Then there's the variance of the variances?
That's right.
Like,
The variance, see below. They can't even fit it in the table, right?
It's nasty.
It is, do you want to even, should we see below, or is that going to ruin everybody's Friday before spring break?
Well, they have a week to recover.
but it's like, how do I pick a number, or like, how do I make an informed decision about what this is supposed to be when this is so convoluted?
The way that you anchor it is to, again, the idea of data. If you have a guess as to what your covariance matrix should be, right? You use that for psi, and you use effectively your degrees of freedom, or your number of variables minus 1, or number of variables is a very uninformative. But the bigger nu gets, the more informative this prior gets for it.
Is psi the dimensions of all the elements in the matrix?
It's a
Or is
matrix
there-
itself. It's effectively like if you were to say, I have a covariance matrix, and I were to go randomly grab a bunch of covariance matrices, it would look like sort of the mean of that covariance matrix when you have nu bigger than 1 plus.
No, but you're trying to find a best guess for all the variances and all the covariances. So like if I have 3 variables, that's 6 things. So
Right.
psi 6 by 6.
3 by 3.
It's still 3 by 3.
Right.
But you didn't put anything on the off diagonals.
I didn't on purpose because that allows me to have uninformative priors on the covariances.
Okay, so then those are coming from whatever correlation rule you just said.
Right.
Okay, and then they back engineer.
That's right.
That's why I was asking why he was making it independent.
Yeah. Well, we haven't gotten there yet. We're on a break. Do you want to take a break and just? Should I just put up the math behind it, or is that bad? Should I put up like? Hold on. Let's go. It's like, where's a beach near you? Here we go. There we go. Let's just go and look at that. Atlantis, Bahamas. There we go. Oh wait, no adverts. Let's go here. There. Ah. All right, let's take 10 minutes. Come back a little bit after. How about 10:52? Let's try that.